Good day. Our topic for today is about differentiability and continuity of a function at a given number. So in this topic, we're going to identify if the given function at a given number is differentiable or continuous. Okay? So how do we identify differentiability and continuity of a function given at a given number? So first, let's define how a function be differentiable, okay? Or how do we consider function to be differentiable? By definition, a function f is said to be differentiable at x is equal to x of 0 if its derivative, which is the f prime of x of 0 at x is equal to 0, exists. So which means we need to verify that derivative of a certain function at a given number x is equal to 0 is existing. If it doesn't exist, therefore the derivative does not exist, therefore the function is not differentiable. All right? And how do we consider that, or how do we know that the derivative exists? So we're going to explain that on the next slide. But before that, now let's consider definition number 2. A function f is said to be differentiable on an interval, open interval, AB, if f is differentiable at every real number in the given open interval AB. Okay? And number 3, if a function or a function is said to be differentiable everywhere, if it is differentiable at every real number in a given range, all right? Sorry, in a given domain, or the values of x. And of course, the value of x here is the real number. So whatever value you pick from the set of real numbers, then the function is differentiable at a given number, whatever that number be. Okay? And now, let's define the one-sided derivative. We will be using this definition to show that a given function is differentiable. And when do we say that it is differentiable? So here it is. The first condition is this. If the function f is defined at x of 1, again, it is defined at x of 1, then the derivative from the right of f at x of 1, denoted by this. Okay, so the derivative from the right of f at x of 1 is defined by this equation or formula. So this is equal to the limit of f of x of 1 plus delta x minus f of x of 1 all over the delta x as delta x approaches 0 from the right. Or we can also use this formula or equation to show that the derivative from the right exists. Okay, so here the formula here is the limit of f of x minus the function f of x of 1 all over x minus x of 1 as x approaches x of 1 from the right. So this is the definition of the one-sided derivative from the right. All right, we can either or we can use either of these two, but I prefer this because this is simpler than the first one. Okay, and for definition number 2, if the function f is defined at x of 1, then the derivative from the left of f at x of 1, denoted by this notation or this symbol, is defined by this. So it's just actually similar with the first definition. It's just that we change the position, okay, or the position of the values of x that we will be using to get its limit. So we're now getting the derivative, all right? Or we can also use this instead of the first one. And I prefer, again, the second one. Now, and make sure that the limits on these two sides, all right, are existing, okay? Or the derivative exists. Now, when the derivative exists, derivatives of both left and right of f at x of 1 exist, all right? So then we could say that the function f is differentiable. Again, if the derivatives of both sides exist and at the same time they are equal, then the function f is differentiable. Now, whenever the derivatives of these two exist, but they're not equal, okay, let me write it down. So again, if we have if the derivative from the right, okay, here we go. This is from the right is equal to the derivative, okay, plus from the left, from the left, and they're both existing, then f is differentiable. Differentiable, okay? However, if the limits, the one-sided limits of f from the right and from the left, x sub 1 from the left are not equal, though they exist, but they're not equal, then f is not differentiable. Okay, understood? And of course, if one of them is not differentiable, then therefore we could conclude that f is not differentiable. Okay, so these are the two conditions for us to conclude that a given function is differentiable or not. So they should be, their limit should be existing and at the same time equal. Okay, I hope it's clear. So here, from this definition, it follows that the definition f defined in an open interval containing x is differentiable with respect to x if and only if, this is what I said a while ago, the derivative from the left and the derivative from the right at a given number x of 1 exists and are equal. So they should be existing and at the same time the values are equal. And if that is so, therefore the derivative of the given function at a given number x of 1 is also equal to those two-sided limits, okay? Or derivatives, all right? So that's the definition. Those are the two conditions for us to show that the given function at the given number is differentiable or not. And another thing here that we could use to show that a certain function is continuous and differentiable with the use of this theorem. And it says, if a function f is differentiable at x sub 1, then f is continuous at x sub 1. So which means, class, for us to determine that the function or a function is continuous, we need to show first that it is differentiable, okay? So once we found out that it's differentiable, a function is differentiable, check with a check mark here, and it goes to show that the function is continuous, check as well. Okay, again, if the given function was proven to be differentiable, then automatically that function or this function is continuous. Okay, as long as it satisfies the given definition for differentiability. Okay, or we can use the contrapositive or contraposition of the statement of the theorem. So by converting the conditional statement to contraposition, we could say if f is not continuous, correct? Okay, then it goes to show that the given function is not differentiable. All right, this is the conditional statement. And this is the contrapositive statement. And as we all knew, in logic, the contrapositive of a certain conditional statement is logically equivalent to the conditional, all right? To the conditional statement. So either statements are both true, and you can use these both statements to show that the differentiability and continuity of a certain function, or not continuous and not differentiable functions. Okay, I hope it's clear. Everything is clear. Okay. And again, when I say continuous and differentiable, we're talking about at a specific number, x sub 1. Okay, so let's apply the, the theorem and the concepts of differentiability and continuity. All right. Oh, by the way, before we proceed with example number 1, let's just have a short background or a short review of uh, the conditions to become continuous, okay, or for a number to be continuous. Now, let me write here. So let me just change the color. Okay, so uh, to become continuous, or for the function to be continuous, now it needs to satisfy 3 conditions. Number 1, f of x sub 1 or 1 should be defined. Okay, it should be defined or it should exist. And number 2, condition number 2, the limit of f of x as x approaches x sub 1, okay, as x approaches x sub 1 exists. Okay, and how do we show that the limit exists? Of course, based on the definition and properties of limits, the left-hand side, okay, the limit of f of x as x approaches x sub 1 from the from the right should exist, and the limit of f of x as x approaches x sub 1 from the left should exist, and at the same time, they should be equal, okay? So existence of the limit is not complete or is not a valid reason for it to be, for the limit to exist, but they should be equal of value, okay? When we say equal, we are talking about real number value, okay? And now for the last condition, once we found condition 1, condition 2, okay, to be true, then we need to show that f of x sub 1, sorry, 1, not I, is equal to the limit of f of x sub 1, which is x sub 1. Okay, so this will be our final or the last proof or last step to show that a given function is continuous at x sub 1. Okay, guys, so there are 3 conditions that we need to do. So let's just have a recap. For differentiability, there are 2 conditions. Now, the derivative from the right and from the left should be existing and should be equal, okay, for it to be differentiable at x sub 1. And for continuity, okay, or for a function to be continuous at x sub 1, now it should satisfy 3 conditions, these 3 conditions, okay? All right, so I hope we're ready for example. Okay, so let's have example number 1. And the problem is determine if the given function is continuous and differentiable at x is equal to c. So given a certain number c, a real number c. So our function here is what's this? A piecewise function. F of x is equal to x when x is less than or equal to 0, and x plus 1 when x is greater than 0. And we need to check its continuity and differentiability at x is equal to 0. All right. So how do we check its continuity and differentiability, and which one are we going to check it first? Okay. Now for me, since we have already a theorem discussed, all right, which states that differentiability implies continuity, then we could check its differentiability first, okay? We can check if the function is differentiable or not. So as we could imply, or we could, we could directly say that it's not continuous if it's not differentiable, all right? Or you can do either way. You can start with continuity first, then differentiability, or vice versa. So here, let's solve solution. So let's start with Let's start with continuous first, okay? Let's do it one at a time. So letter A, continuity at x is equal to 0. Okay, so for us to show that it's continuous, it needs to follow or to meet the three conditions. Number one condition, we need to show that f of x, okay, which is equal to 0, must be defined, or there must be a certain real number, okay? So let's solve. Now here, f of, okay, let's change the color. Okay, so f of 0 is equal to, so which function are we going to use? That's the first subfunction, which is x, is equal to 0, right? So therefore, it is defined since f of 0 is a real number, which is equal to 0, okay? And condition number two, we need to find its limit of f of x as x approaches 0, okay? And how do we do this? How do we solve for the limit? So number one, all right, so we need to find the limit of a certain, of the function when x is approaching 0 from the left, okay? So when we're talking about the limit from the left of 0, oh, sorry, so let me erase that. There we go. Okay, so from the left of 0, so we're talking about this, the first subfunction, which is x. So this becomes the limit of x as x approaches 0 from the left, since all of the numbers of x or values of x that we will be using or testing are negative numbers, or those numbers or values which are from the left of 0. So this becomes 0, okay? And here, so we have already found the limit of f of x as x approaches from the left of 0, and it exists. So let's check the other side of limit, the limit of the other side of 0. So that's from the right. Okay, since we're talking about positive values here, so we're going to use the second function. So the limit x plus 1 as x approaches 0 from the right. So here, we all knew that this would be, sorry, let's just put our next step here. So we can use direct substitution of 0 to x, since it will not give us undefined or even imaginary value. So this becomes 0 plus 1, which is equal to 1. It exists. However, though it exists, guys, however, these two values, 0 is not equal to 1, thus limit of f of x as x approaches 0 does not exist, D and E. Okay, so here the answer is D and E. All right, and if you want to show the third condition, if it is being met, obviously it's not, because f of x is not equal to the limit of f of x as x approaches 0. Why? Because this is 0 and this does not exist. They're not equal. So therefore, we could say that f is not continuous, right? Okay. And what do we know when we or what can we imply if we know that a certain function is not continuous? Based on the theorem, we could use the contrapositive of the given theorem, and it states that okay. So let's talk about the theorem first. Differentiability implies continuity, and the contrapositive or contraposition of this statement is not continuous implies not differentiable, right? So we have already found that f is not continuous. We're talking about the second statement, and it implies that okay, it implies that f is not differentiable. Right? Okay. However, we need to show that f is really not differentiable. How do we do that? Okay, so letter B. Yeah, letter B. So let's show that it's not differentiable. Differentiability at x which is 0. Okay, for the sake of argument, let's show that it's not really differentiable. Okay, let's use y here. So we have, again, our function is, just to review, f of x is equal to piecewise function x and x plus 1. And here is x is greater than or equal to 0 and x is less than 0. If I'm not mistaken, let's check. Oh, it's wrong. Okay. So here, reversed. Okay, so let's just, so here is less than or equal to 0, and this one is greater than 0. Oh, yeah, less than, greater than 0. Okay, here we go. So let's check for differentiability. So our solution, oh, sorry. So let me just, okay, so let's check for differentiability. Okay, so solution. Now, how do we again show that a given function is differentiable at a certain number? We're going to use the derivative on both sides, or one-sided derivative of the given function. Okay, so we need to show that f prime of x from the right is equal to f prime of x from the left. Okay, so let's do it first. So a, or I, let's talk about f prime of x from the right, which is equal to the limit of the derivatives, or the slope. So f of x minus f of x, or we could have x of 1 here, over all over x minus x of 1 as x approaches x of 1 from the right. Here we go. Okay, and that's all. Okay, so since we're talking about values from the right, now this becomes f prime of, what's this, 0 from the right is equal to the limit as x approaches 0 from the right. All right, and we have f of f of x minus f of 0 all over x minus 0. Okay, so let's simplify. Limit as x approaches 0 from the right. What is f of x? So since it's from the right, so here we go. We're going to consider the positive values, or from the right of 0, values of x. That's x plus 1. X plus 1 minus, what is f of 0? F of 0 is, we're going to consider this subfunction, since this is a function value when x is equal to 0, and 0 is part of this sub function, all right, which is x. So therefore, it is just 0. Why 0? Because when x is 0, x is 0 is here. So we have x minus 0. So in this case, we have the limit x plus 1 over x as x approaches 0 from the right. And if we're going to simplify this, this is equal to 1 plus 1 over x as x approaches 0 from the right. Okay, and look at this, guys. This is equal to undefined. Why? Because 1 the limit of 1 over x as x approaches positive infinity, 0 from the right is equal to undefined. So this becomes 1 plus infinity, or undefined becomes undefined. So therefore, this is equivalent to undefined. So since one of the conditions for a function to be differentiable at a certain number is that now the one-sided limit should exist, okay? Since at the very beginning it didn't exist already, therefore we are so sure that it's not differentiable, okay? But for the sake of argument again, let's find out. Let's find out the second condition. Let's see what's going to happen. The derivative of f, the derivative of f of x from the left, okay? So we need to check on this. So that's f of, let's put it here. The limit as x approaches 0 from the left, f of x minus f of 0 all over x minus 0. Oh, by the way, I'm using the second equation or formula to determine the differentiability of a given function at a certain number. So here, f prime of x from the left is equal to the limit as x approaches 0 from the left. And what is the f of x that we will be using here? So we're talking about values of x which are on the left side of 0. So let's check that here. Here we go. So all the values that which are less than 0 are on this function x. So we will be using this x. And of course, the function value when x is equal to 0 is equal to 0. Okay, and x minus 0. So this becomes the limit x over x as x approaches 0 from the left. And this is just equal to the limit of 1 as x approaches 0 from the left is just equal to 1. And we knew that f of the derivative of x of 1, by the way, this is 0, since we have already substituted. And this is x of 1. Okay, from the right is not equal to the derivative of f of x, so 1 from the left. Why? Because this is undefined and this is 1. And of course, undefined is not equal to 1 because 1 is defined, right? A well-defined real number, okay? While infinity is an undefined expression or symbol. I mean, it is a symbol for undefined value, okay? Function value. Okay, so therefore, since it did not meet the conditions to be differentiable, therefore, f is not differentiable at x is equal to 0. Okay? Since f is not differentiable at x is equal to 0, it does not necessarily mean, guys, that the function f is not differentiable to all values of x. It is not just differentiable when x is equal to 0, but in other values, now they are differentiable. But of course, we need to check that. We need to verify using the conditions. Okay, and let's check if we have the same conclusion. Okay, with the use of the concept and the theorem that we discussed before. Here we go. So, as we said earlier, since f is not continuous, therefore f is not differentiable. And that's what we found out, right? So therefore, our theorem is actually true. And it could help us to easily identify if the function is continuous or not, or differentiable or not. Okay, I hope everything is clear. And let's work on the next problem, right? So the next problem is this. Determine if the given function is continuous and differentiable at x is equal to c, and f of x is equal to this piecewise function again. Okay, so let's work on, let's use white now. Okay, so let's try solution. Let's try continuity. Okay, let's test for continuity at x is equal to 1. Okay, here we go. So again, we have three conditions to check if a given function is continuous or not. All right, but in short, we just need to show that f of x sub 1 is equal to the limit. Oh, this is equal to the limit of f of x as x approaches 1. This is the only thing that we need to show for us to say that it is continuous. Okay. And of course, we need to check this, and we need to check this, and of course, combine these two. We need to check this. Okay. Oh, a human being. Okay. So first, now let's consider the condition number 1. Okay. Condition number 1, we need to check the function value at x sub 1. Okay. It should exist. So when x is equal to 1, f of 1 is equal to, okay, so which subfunction are we going to use? Of course, the second, because, oh, sorry. I think there's something wrong with the given condition. Sorry. All right, so this must be 1. This must be 1. This must be 1. Okay? Okay, here we go. So, right, let's use magenta here. So f of 1, of course, f of 1, x is greater than or equal to 1. We're going to use again the second subfunction. So that's 1 minus 1 square. This is 0. So therefore, the function value at x is equal to 1 is 0. Correct. Okay. So what we need to do now is to check for the limit, if it exists or not. All right. So condition number 2 for continuity, the limit. So we need to test for the existence of the limit of f of x when x is approaching 1. And again, we're going to check the one-sided limits values, okay, of the function f. So we have the limit of f of x as x approaches 1 from the left. Let's talk about from the left first. Okay, from the left, so when x is less than 1. When x is less than 1, we're going to use the second equation, the first subfunction here, which is x minus 1. So therefore, this becomes the limit x minus 1 as x approaches 1 from the left, correct? And this becomes, let's write it here, this becomes 0. So 1 minus 1 is equal to 0. Okay, it's 0. So therefore, the limit of f of x as x approaches 1 from the left is equal to 0. Now, let's verify. Oh, by the way, it exists. We're glad that it exists, but we need to check if the existence of limit from the limit of f of x from the left of 1 is equal to the limit of the function as x approaches from the right, diba? Of 1. So the limit of f of x, as x approaches 1 from the right. Here we go. So we have the limit as x approaches 1 from the right. And which function? X should be greater than or equal to 1 or greater than 1. You will be using this. So we have x minus 1 square. So here we go. Now we can simplify this, okay? We can do direct substitution. So this becomes 0 minus 1. Oh, why 0? It should be 1, sorry. So this must be 1. All right, and we have 0 squared is equal to 0. And it exists. The limit of f of x as x approaches 1 from the right is equal to 1. So if we're going to check, both limits are equal to 0, and they're both existing. So therefore, we could say that For continuity, the limit as x approaches 1 from the left is equal to the limit of f of x as x approaches from the 1 from the right. They're equal values of equal values. So therefore, we could say that function f is continuous at a number 1, or x is equal to 1. Okay, so continuous. And the question here is, how about differentiability of the given function? Can we now say that the given function is also differentiable? Okay, now based on the theorem, okay, let's review the theorem again. So we have differentiability implies continuity. So it means we cannot use this theorem to show or to imply that it is also differentiable. We cannot use this. However, let's work on the contrapositive or contraposition, okay, statement of the contrapositive statement of the given theorem. So not continuous implies not differentiable. However, we found continuous, so therefore we cannot also use this. So what we need to do is to check the given function, or we could also sketch the graph if you want to. Okay, so now let's show, all right, or illustrate and show the solution to show that f is differentiable. F is differentiable, question mark, at x is equal to 1. And how do we do this again? Of course, we need to show that the derivative of x of 1 from the left is equal to the derivative of f of x of 1 from the right, okay? And if this is what we got, then therefore f is differentiable at a certain value of x, which is 1. So let's find out. So f prime of x of 1 from the left is equal to the limit of f of x minus f of x of 1 all over x minus x of 1 as x approaches x of 1 from the left. Okay, now since we're talking about all the values of the x from the left of 1, so let's check the function again from the left of 1, so that's x minus 1. Okay, so that's limit x minus 1 minus f of 1 all over x minus 1 as x approaches 1 from the left. Okay, and what is the function value when x is equal to 1? So when x is equal to 1, our function value is 0, right? So we are using the function value. Okay, so it's 0. So let's continue. So we have f of prime of x, or this becomes 1 already, from the left is equal to, we have x minus 1 minus, and what's the function value of f of 1 again? It's equal to 0. So therefore, this is 0 all over x minus 0. The limit as x approaches, oh, sorry, why 0? It should be 1. Okay, guys, so let me just correct this. Okay, our value of x is equal to 1 here, correct? Okay, so as x approaches 1 from the left, 1, so let me check that. Yeah, it's 1. So we have the limit of x minus 1 over x minus 1 as x approaches 1 from the left, and this becomes, we can cancel, this becomes 1. So the limit of 1 as x approaches 1 from the left is equal to 1. So f prime of x, or 1, from the left is equal to 1. So it exists, okay? It exists, and of course, we need to check that the f prime of x from the right should be also existing at the same time it's equal to 1. And we're hoping for that, okay? Hoping, okay. So let's work on the second part, or the right-hand side. So f prime of x from the left is equal, sorry, from the right is equal to the limit as x approaches 1 from the right, f of x minus f of, oh, sorry, x of 1 here, x of 1, x of 1. So since we're talking about the general form, x minus x sub 1. Okay, so let's go. Limit. Okay, and what is the, okay, so let's just write here, copy. And this is f of 1 over x minus 1 as x approaches 1 from the right, right? Okay, it's true. So since we're talking about all the values of x which are at the right side of 1, so let's check the function. Right side of 1, so that's x minus 1 squared. X minus 1 squared. So limit of x minus 1 squared, okay, based on the given values of x that we're trying to use here. And what is f minus 1? F of 1 equal to? That's the function value, right? So the function value is equal to 0 because based on the given, we're going to use the first subfunction. So 0 over x minus 1 as x approaches 1 from the right. Okay, so let's simplify. Oh, we don't have space. All right, so don't mind this yet. So we have f prime of x from the right is equal to the limit as x approaches 1 from the right. There we go. So that's x minus 1 squared over x minus 1. So we can simplify this. And the limit x minus 1 as x approaches 1 from the right. And this becomes 1 minus 1 is equal to 0. So f prime of x from the right is equal to 0. So we've found, guys, that f prime of x from the left is equal to 0, and 0 is also the value of f prime of x from the left, from the right. So they're existing and they're both 0, so they're equal. Therefore, it satisfies the given condition for the function f to be differentiable at a certain value of x, which is equal to 1. Okay, so therefore, we can now say that f is differentiable at x is equal to 1. Okay, understood, guys? So here, let me just, oh, by the way, the limit is 1, sorry. Okay, so this is wrong. My goodness, I'm happy that I checked that. Okay, so let's recheck that. Here we go. The f prime of x from the left is equal to 1. Okay, let's verify. Yeah, it's equal to 1. Sorry for that. And 1 is not equal to 0, which is equal to f prime of x from the right. So since they're not equal, therefore f is not differentiable at x is equal to 1. Okay, here we go. This is final. So f is not differentiable, but f is continuous. So which means, guys, continuity does not imply differentiability. It could be differentiable, it could be not differentiable. Okay, it depends on the given function. Okay, so here is the solution for example number 2. And let's work on the next example. Okay, again, this example number 2 is continuous. So let's write the summary. Okay, so we will not be confused again. Sorry. Okay, so f is continuous but not differentiable at x is equal to 1. So this is our conclusion. All right? Okay, so now let's move on to this example. I'll just erase everything in this so as we could work on the given example number 3. Okay, so in example number 3, determine if the given function is continuous and differentiable at x is equal to c. So here we have this function. Okay, now let's try to change our plan on how to attack on this problem. Let's work on differentiability first. Okay, it's up to you. Which one would you like to solve first? But again, I think it would be helpful to determine differentiability, because once you identify differentiable functions, then you can conclude that it's continuous based on theorem. Okay, that says differentiability implies continuity. Okay, so differentiability, test for differentiability. Okay, so our function is this. And again, how do we test for differentiability, or how do we determine if a function is differentiable or not? Of course, we're going to use the one-sided derivatives, okay? Oh, by the way, class, better if we're going to sketch the graph, because seeing the graph or just looking at the graph helps a lot. Okay, so let's just sketch the graph. So let's say this is -2. Okay, and let's make use of another color here, magenta. And if x is equal to -2, this function is equal to -6. So let's say -6 is here. So the point is here. And since it's a parabola that opens downward, so here, it should be, the vertex is at the 0 origin, somewhere here, something like this, right? And of course, it's heavy. Why? Because -2 is part of the first subfunction. Okay, and how about 6x minus 5? 6x minus 5. So when x is equal to -2, that's -12, -17. There we go. So that's lower than this, right? Okay, so let's just extend this. Okay, and change the color to magenta again. So that's, if x is equal to -2, this function becomes 6 times -2, -12, minus 5, -17. So -17, it's here. Okay, so there we go. So it's hollow. And of course, it should pass through -5. So, and it has a positive slope. So it's rising from the left to right. Here we go. Oh, sorry. It should be hollow. All right. So this is our graph of the given piecewise function. And look at this, guys. This is already a non-continuous function, right? And when we say non-continuous function, what does it mean? By the contrapositive statement of the theorem, it only means that not differentiable. So not continuous implies not differentiable. So we have already an answer, okay? We have already answered the problem, but it's better to show it mathematically by using algebra, okay? The solution, and of course the graph is part of the solution, but we better do it this way, okay? At least we have a guide here. All right, so we know that it should be non-differentiable, okay? So as for differentiability, again, we need to check the derivative of x sub 1 from the left should be equal to the derivative of x sub 1 from the right. Okay, and they should be existing, of course. So let's work on the left-hand side. So f prime of x sub 1 is equal to the limit f of x minus f of x sub 1 all over x minus x sub 1 as x approaches x sub 1 from the left. Okay, so look at this, guys. Let's analyze that here. Oh, we're talking about the derivative here. We're talking about the slope here, right? So what's happening to the slope when the slope of the tangent lines from the left side of -2? So let's make this of the white color. The slopes are all positive. It's rising, correct? They're all here. So it's positive, it's rising. Okay, but let's not depend on the graph. Let's use the algebraic way to do that. Okay, so here, again, f prime of x sub 1 negative is equal to, so we have already shown the general form. Since it's negative, sorry, it's on the left side, therefore we're talking about the first subfunction, the -3x squared. Okay, and okay, so we have the limit of the function. So we're going to make use of this because this in this function we're going to get all of the values of x which are less than -2. Okay, so this becomes -3x squared over 2 minus, oh, what's the value of the function? The value of the function when x is equal to -2 is this. Okay, let's solve that. Oh, sorry. So we have f of -2 is equal to -3 halves 2 squared is equal to -6, f of -2, such that we have a guide here. So this is -6. Okay, x minus -2 as x approaches -2 from the left. Oh my God. Okay, there are lots of signs. So here we go. Let's simplify this. So that's limit, oops, sorry. So let's continue. So let's simplify. We have the limit, oh, again, but anyway. So we have as x approaches -2 from the left. Let's simplify the numerator. So this becomes a -3x squared minus or plus 12. I already simplified, guys. This becomes 2 times x plus 2. Here we go. Let's recheck x plus 6, negative. Okay, here we go, plus. All right, here we go. So let's continue. Oh, it's ugly. Okay, so let me just write. Okay, let's factor this out. This can be factored into -3, x plus 2, and x minus 2. Okay, and 2 times x plus 2. Okay, again, once I factored out this -3, this becomes x squared minus 4, and x minus 4 can be factored into this, right? So here, I can simplify. I can cancel out x plus 2 here, and what remains is this. So let's write that here. So the limit -3 over 2 x minus 2. All right, and as x, here we go again, -2, negative. So we can do direct substitution. -3 halves, -2 minus 2 is equal to, this is equal to what? -4, -12, so +6. So the value is equal to 6. The derivative of, sorry, -2 from the left. All right, so it exists and the value is 6. So we need to check the other side, the right-hand side of the given equation. What is that equation? This equation. So we need to check this too. Okay, so let's work on the right hand side. So that's the derivative of x sub 1 from the right is equal to the limit. Okay, you don't need to do this, guys. If you are already aware of what's going to happen, you can go directly to the equation that you are going to solve. Okay, so that's f of x minus f of x sub 1 all over x minus x sub 1 as x approaches x sub 1 from the right. Okay, again, it's from the right, so we need to check. So we're going to make use of the second function, 6x minus 5. So that's the limit of 6x minus 5 minus, what is the function value again of f of, what's this? Okay, let's try write that here. So as x approaches -2 from the right, so -2 all over x minus -2. Okay, so let's simplify this. The limit of 6x minus 5. Okay, what is the value of f of -2? So we solved that earlier. Here we go, it's -6. So minus -6 all over x plus 2 as x approaches -2 from the right, correct? Okay, so let's simplify again. So x is approaching to -2 from the right. Oh my, so this one is 6x plus 1, x plus 2. Here we go. Okay, so since we cannot simplify this anymore, and if we're going to substitute the value, this will give us an undefined value, right? Because 6x plus 1 over x plus 2 is unsimplified anymore, unless we're going to make it or express it in terms of what? If we're going to divide this expression, we still get an undefined value here. So this becomes the limit of -12 plus 1 over -2 plus 2 as x approaches -2 from the right. This becomes what? Oh, sorry. Since I already substituted the possible values of x, then I should be removing the limit expression or notation. So let's go back to white. And this becomes what? -11 over 0, and this is infinity. Okay, on the right. All right, well, actually it's negative infinity because -11 over this is positive, since -2 here on the right of -2. Okay, so we found out that f prime of x, sorry, it's -2 from the right is already negative. It doesn't exist. And however, we have shown a while ago that the derivative of f of, okay, so this is -2 from the left is equal to, let's work. Okay, here it's 6, correct? It's 6, which is not equal to negative infinity, which is equal to, oh my, -2 from the right. They're not equal. Therefore, the function f is not differentiable at x is equal to -2. Now, f could be differentiable at some values of x, but not in -2. Okay, so we are now going to check that if that is true. And a while ago, we said the function, the graph of the function is not continuous. Therefore, it implies that it is not differentiable. And we've shown that here, that it's not really differentiable, correct? So it's true. And this is correct. Okay, so we have already tested its differentiability. Now let's test its continuity. All right, so let's check on that. And since we don't have space, let's make use of Okay, this this slide. So letter B, or guys, you can just state your reason since the function is not differentiable anymore by theorem that states that, or we could just say since f is not differentiable at x is equal to -2, then f is not continuous at x is equal to -2 by the sorry, not differentiable. Wait. So continuity, differentiability. Oh, sorry, guys. This is wrong. Okay, we're not supposed to be doing this way because differentiability implies continuity and not continuous implies not differentiability. Okay, so we must have shown first the continuity. But anyway, okay. So again, this is wrong. So let's work on the algebraic way of showing that it is not continuous anyway, okay? So letter B, continuity. I'm imagining things at x is equal to -2. Okay, so again, for continuity, we need to check on the three conditions. And we need to show that f of x sub 1, the function value at x sub 1 is equal to the limit value of f of x at x approaches x sub 1, right? So the first condition is f of -2. So what would be the value of the function if f is equal to, if x is equal to -2? X is equal to -2, we'll be using this, and we have solved this already. And we found out that it's equal to -6, as we saw before. All right, so -6. Okay, so condition number 2, the limit of f of x as x approaches x sub 1, something, just like it should exist. Okay, and for us to do this, we need to show that the limit on both sides exists. So f of x approaches -2 from the left muna. Okay, so from the left, when the values of x are less than -2, so which function are we going to use? Here we go, -3x squared over 2. So 3x squared over 2. X approaches -2 from the left. Okay, so here we can do direct substitution, and this is equal to what? This is equal to 6, -6. So that's -3 over 2 times -2 squared. This is 4. So -6. That's limit. F of x as x approaches -2 from the left. All right, so it exists. And we need to check if the limit from the right is existing, and at the same time, if it's equal to 6. So let's work on the next slide. So we have the limit of f of x as x approaches -2 from the right. Okay, so we have the limit of -2 from the right. And which function are we going to use? So we have from the right is 6x minus 5, of course. 6x minus 5. Okay, so here it becomes what? We can do direct substitution. That's 6 times -2 minus 5 is equal to -17. That's the limit of f of x as x approaches -2 from the right. So if we're going to check, guys, the limit, the limit of f of x as x approaches to -2 from the left, which is equal to, what's the value? -6, is not equal to -17, which is the limit of f of x as x approaches -2 from the right. So therefore, since although they exist, but they're not equal, we could say that f is not continuous. Is not continuous at x is equal to -2. And we can conclude that f, therefore f is not continuous. And what was our, yeah, it's not differentiable and not differentiable, correct? And this was our assumption a while ago. Our assumption a while ago was with the use of the graph. Okay, when we sketch the graph, it is not continuous, therefore it's not differentiable. And we've shown it correctly. All right, we've shown it correctly that it's true. Okay, so therefore we're done with that example. And let's work on the next example here. Okay, so let me just check this. Okay, here we go. Now let's work on the last example. I think this is the last example. Let me just check. Yeah. Okay, let's work on the last example. Let me just add another slides. Okay, yeah, this would be the last, yay. Okay, this would be the last example. And let's work on this. Okay, again, you better sketch the graph for you to easily identify if it's really continuous or not, or even not differentiable or differentiable. So x is equal to 1. Let's sketch our graph here. It's just a sketch, all right? So x is equal to 1, it's here. And let's work on this. So if x is less than or equal to 1, x squared plus 2x. So x squared plus 2x, that's x is equal to 0 and -2, correct? So let's plot the points. Let's plot the points. 0 and -2. Let's say -2 is here. And there we go. So it's a parabola that opens upward. Okay, and the what's the vertex? So that's x squared plus 2x plus 1 minus 1. So that's x plus 1 squared minus 1. Therefore, the vertex is -1, -1. Okay, here we go. Here. And if x is equal to 1, what's the value? It's equal to 3. Let's say 3 is here. So the point is here. There we go. So less than 1. Oh my. Okay, and this is shaded or heavy because x is 1 is equal to x here. Okay, or 1 is one of the values of the domain here in this function. Okay, here we go. And let's work on the next function. Let's sketch its graph. So let's make use of cyan. Let's try this one. For x minus 1, when x is greater than 1. So when x is equal to 1, it's 3. Yeah, it's 3. And it's hollow. And its slope is up, right? Something like this. Okay. So as we can see, guys, this is continuous. Okay, but continuity does not imply differentiability nor not differentiability. Okay, so we need to test on that. All right, but we are so sure that f is continuous. Okay? However, if the problem states that you need to show the solution for continuity by algebraic solution, not by graphing, then we need to do so. Okay? So let's work on continuity, but we are so sure that it's continuous. Okay, so we have a continuity. Although it's quite long, or it's really long, but we need to do that. Okay, we need to follow instructions. Okay, so condition number one, we need to find the function value. Function value should exist or should be defined. So f of 1 is equal to what? And f of 1, we're going to use the first sub function. So that's, let's say x squared plus 2x. So f of 1, the function value is equal to 1 plus 2, and it's equal to 3. So therefore, f of 1 is equal to 3. And again, we need to show that f of 1 is equal to the limit of f of x as x approaches 1. And if we have shown this, then it is continuous, correct? But we said that, yeah, it is continuous. So therefore, this must be true. And for us to do that, we need to find the second condition, which is the limit of f of x as x approaches 1, all right, should be defined. It should exist. Okay, so we need to get the limit, the one-sided limits values, one-sided limit values. So f of x as x approaches 1 from the, okay, positive from the right. So this becomes the limit. And what is the function that we're going to use? We're going to use the 4x minus 1. So 4x minus 1 as x approaches 1 from the right, and this is equal to, we can use substitution. 4 minus 1 is equal to 3. Therefore, the limit of f of x as x approaches 1 from the right is 3. So it exists. And we knew that, oh, they are equal, but we're not yet done because we need to check the other side of the limit value, okay, or the limit value of the other side. Okay, so we have, let's continue. The limit of f of x